Okay, so we're basically going to cover three things today. So first is the Stern-Gerlach experiment, which is kind of the key piece of experimental evidence that lets us know that we need quantum mechanics. And we'll spend a little bit talking about the quantum formalism, and then we'll do the particle in a box. So the first thing I want to talk about is Stern-Gerlach experiment. And this was done by Stern and Gerlach in 1922. And so the setup is that you have some furnace. So like maybe here's some like flames in here. And the furnace, so this is the furnace. And inside the furnace we have silver atoms. Right. And you have some plates with some holes in them, just to make sure that like you get, so the silver atoms will get excited, and then hopefully some of them will be excited enough that they gain some velocity and they kind of waft outwards in the box. And so you put these holes here. This is the collimator. I couldn't find details on the type of collimator they use in the experiment, so just basically think of this as like just some holes that make sure that like the particles that make it to this part of the experimental setup over here will be mostly going in parallel lines to each other. And so the next component is a big magnet. And so the magnet has kind of a funny shape to it, but just to kind of create the most intensity possible in a small space. And so here's the South Pole. And we have some magnetic field lines. So this is like the other view. There's magnetic field lines going like this. And so this is the magnetic field, which we use a B in physics usually. And then over here, there's going to be like a target or like a detector plate. And so the basic premise is you have the silver atoms that should be coming out of here in roughly a straight line, right? And so classically speaking, so here's over here. The reason they chose silver is that silver has one valence electron. So the magnetic moment is basically going to be proportional to the spin of one electron, right? And so the idea is like classically, we should have a random distribution because all the atoms are moving around basically randomly. So we expect random distribution for, I guess what I'll call is the magnetic moment in the z direction, mu z. So you might think of, okay, like for all these atoms, they might have some little magnetic moments that look like this, or like this, or like that. And based on how much that aligns with the magnetic field, so we have these field lines, and so we expect that the force due to the magnetic field is going to be proportional to this dot product, where mu z is this kind of random vector that's based on the spin of that one valence electron, and this dot product will vary randomly, right? So classically, we expect to get a full range here. Right, so we see like all of the mu z between minus the spin of an electron, or the magnetic moment of this electron, and the positive one. So it's positive. Okay. And so in reality, we see this. basically. So this is what really happens. And what this observation says is like basically like the spin of all these silver atoms ends up being quantized. Like there's exactly two possibilities that really occur instead of seeing the continuum for all these values in between that we expect in the classical case. Okay. And specifically, so I'm going to change from talking about this magnetic moment to spin. They're proportional, but the numbers are nicer this way. We see that, instead of like all ranges, like SZ in a range, we see that SZ is one of two things. So it's either minus h bar over 2 or plus h bar over 2. Right. And so what is this quantity h bar? So in classical physics, we have this energy frequency relationship for like light and like other radiation. And so, like it's all radiation, you know what I mean. And so we have like, classically, E is h times frequency, energy is this constant h times the frequency. And when you adjust your frequency from being in like linear units to being in angular units, you get this constant h bar. So this is the angular frequency. And we have this relationship where h bar is h over 2 pi. And this is roughly, what is that? 6 times 10 to the minus 16. Minus 16. And this thing has units of electron volts seconds, which I won't go into for the sake of time. Okay. So we know that the electron spin is quantized. That's what we learned from this experiment. So what does Stern and Gerlach do after this? So after that first experiment, they did some sequential Stern and Gerlach experiments. So the first one, now I'm going to draw these in like a 2D schematic way, is so you have your furnace, right? And then you have a Stern-Gerlach apparatus, which is the apparatus that I just erased. And it's oriented in the z direction. So the axis between like the north and the south part of the magnet are like aligned with the z-axis. And so as we just saw, like there's going to be one beam of atoms that's going to go down, and so I'll call that SZ minus. They have the minus h bar over 2 spin. And so let's say we take these ones, we don't want them anymore, we send them into a wall. And we take our SZ plus part, so the ones that are all lined up this way, so like these guys look like this, as opposed to these ones that look like this. And let's put them through another Stern-Gerlach device. So, hypothetically, if what this gate was doing was just like kind of just giving them a random spin along the z-axis, then we expect to see two components coming out again. But what we see is that instead we get a bunch of these guys, like SZ plus. So this is, like full intensity. And there's nothing. So I'll say that SZ minus is missing. And so this is like some kind of idempotency, which should remind you guys of like projecting onto a basis. Right? If you project onto a basis once, then if you apply the projection operator again, nothing changes. You've already projected onto your basis. All right. So maybe I'll come over here now and draw another one of these. So this one's a little bit more interesting. So we have the oven. And so we get, one line of silver atoms, and we put it into a device that's aligned along the z-axis. And so we throw away the downward pointing part. These ones, we send them into a wall. We don't want them. And so we take these ones that are all aligned upwards. And now we let them interact with an apparatus that's pointing in a horizontal direction, perpendicular to the z direction. So we'll call this SGX, right? So if this one, the gate looks like this, now we might be doing something like this. We turned it sideways. And so now what happens this time is we get two beams, which I'll call SX minus and SX plus, which are actually going to be like kind of like right and left, right? In terms of what their spin is. And this right and left that I'm drawing here are kind of perpendicular to the direction of travel, like into the board and out of the board. And these will have equal intensity. And so what's happening here is that you have, it's like you're projecting onto one basis, like onto the z basis, and somehow like the basis for like the x spin is perpendicular. So one that draws like not super scientific, but it's like a schematic picture. And so you can kind of think about it like this, where this is like SZ plus. So that's like along the z-axis, and like this is like SZ minus. So they all have random spin initially, and when we put them through here, it forces them to project onto a basis. So half of them, just by chance, project onto this one, half of them project onto this basis vector, and then when we send this one beam that are all projected onto this basis vector into this other like apparatus, the basis for like the x direction is like incompatible. So the way you might want to draw that is like this, just to think about it. And so maybe this one's SX plus and SX minus. Right, so now if you think about projecting this vector onto this new basis, you're going to get components that are equally along each of the two directions. So like this thought process of like, okay, like we have different incompatible bases and we're projecting onto one than the other is kind of the moral of the story here. So there's a third experiment that I'll draw over here. So this is the last one they did, or the last one that was in the book at least. So it's just like what we did over there. So we take this collimated beam where they all have the spin pointing up in the z direction. We put it into a device oriented in the x direction. So we get our two equal beams. I'll call them XX plus and SX minus. So we send this X minus beam into a wall again. And so let's take these ones that are all pointing right now and put them into an SGZ block. All right. So you might expect, there's two things that might happen, right? We know that before these guys went into like the X measuring device, that as far as the z-axis is concerned, they were all pointing up, like along the z-axis, right? And so you might expect that like coming out of here, we would only see, a line that are still in that alignment, right? But it turns out that we actually, again, get two equal parts. So these are going to be equal in intensity. And so the key thing here is that measuring on an incompatible basis destroys info about the previous basis. Previous basis. Right. And an important aspect of this is that this tells you that if two bases are incompatible, which basically just means that they're different, then you can't measure on the two of them simultaneously, right? Because they're fundamentally incompatible somehow. Right, any questions about this part before I go on to the formalism? Okay, so I'm gonna erase the board. Okay. So now we're going to talk about the formalism. So I already kind of given away that the basic idea is like the state is represented by a vector, and when we do measurements, we're like projecting onto different bases. And so the formalism captures that. So the first kind of axiom is that the state of a system is represented by a vector psi in L2. And specifically, I'm going to write this space to C. Right, we want square integrable functions that are taking inputs in space. So this might be R, it might be R3, and their output is complex. And we have the notation as follows. So this is a vector. This is a covector. And then together, like something like this represents the inner product. So we take a covector and we give it a vector as an input, and this has the normal inner product on L2C, where the star denotes the complex conjugate. And R is going to be my default variable for integrating over space. So this is our inner product. So 2, what do the values of psi actually represent? We have the Born rule, which sounds like an action movie title or something like that. So this is the probability. So when we take the magnitude of this complex number, in the physics parlance, you'd usually call this a probability amplitude. And so this is the probability of observing a particle, or the particle described by this wave function, between x and x plus dx at time t. Right, so what does it mean like between x and x plus dx? It doesn't really mean anything, you have to integrate it. So if you wanted like the probability that, x is between a and b, then you just have to integrate this quantity. Right. Okay. And matching up with this, so as a consequence of the above, we require that the norm of psi squared is 1. So this is our normalization constraint. Okay. Okay, we'll pause for a second. So the next thing is the observable variables. So the fact that we can represent a state as a vector in Hilbert space, and like this interpretation over here, like these are basically axioms of the theory. And this is another big axiom, which is that observable quantities QTYs, are represented by Hermitian operators. So the first thing is, okay, like what is Hermitian? So Hermitian means like, so A is Hermitian if its conjugate transpose, which I'll represent with a dagger, is equal to itself. Is that unitary? I think, yeah. Okay. And why? So Hermitian operators, Hermitian matrices have two nice properties. And so the first one is that, so what I want to say is that, okay, so one, Hermitian operators have real eigenvalues. Right, so the eigenvalues of our operator are going to correspond with the value we actually observe. And so like momentum, energy, those kinds of things should have real number outputs. And that's why the Hermitian operators are nice. And the next thing is that their eigenbases are orthonormal. So that's pretty good. Okay, so for an observable quantity, so we have some observable variable q and an associated operator so Hermitian operator q hat, where we use this like vector hat to like represent like the operator that corresponds with this variable q. The expectation value so in the probability theory, you'd see this as like the expectation of q. And in quantum mechanics, you usually see this notation. So like the expected value of q is going to be this thing. Where this is some more of the Dirac notation that I introduced earlier. And so let me do some examples. Okay. So one-dimensional examples. So the first thing is position. So position is represented by x, right? And so the operator that corresponds to position is just x. So the expected value of position is going to look like this, which will just be in one dimension, this integral from minus infinity to infinity of the conjugate of psi. That's all right, everything with variables this time to be precise. Right, so this is something pretty concrete that we can compute for most simple wave functions. And we have momentum. So P is for momentum. And the momentum operator looks like this. And specifically, I should use a partial derivative, because our wave function can vary as a function of time. So this will be partial x. And so, and if you've taken or you're taking like Lie groups and Lie algebras, then momentum being the derivative should maybe have the right flavor. You have to think about it a little bit. I can explain after, but this makes sense from like a Lie group's perspective. And so the expectation of momentum, we do the same kind of thing. So I was at p hat again, but I can just put it in directly. And so now we have a derivative that's going to act on our wave function under the integral. So in general, it's not quite as simple as integrating a product. But in general, I'm not sure if this is exhaustively true for every possible quantity, but most quantities can be represented as a function of the position, momentum, and time. So that's kind of the general statement. Okay, so we have some statements about how to interpret all this as well. So here's point of interpretation number 1. If you measure Q, where Q is some variable, like position or momentum, you measure Q for a state psi, you are certain to get a value lambda if and only if psi is an eigenvector of Q. So I'm going to use EV with the vector hat for eigenvector of the observable operator Q with eigenvalue lambda. And so, okay, what about the case where it's not an eigenvector? Right. So, which side of the board am I? So I'll just keep writing down here. Actually, I'm going to give myself some more space. Yeah, so in general, let's say we have some eigenvectors with eigenvalues lambda. So this is our spectrum for our operator. And so this is going to be an orthonormal basis. So the EM, is delta MN, which is 0 if M is not equal to N and 1. And in general, our state psi will be some sum of some coefficients times these basis vectors. So this is called Fourier's trick, but it's not so much a trick as it is basic linear algebra, where these coefficients can be computed like this. And so then, now what I'll say is that for a general state, if you measure Q for a general state, the probability of observing the value lambda n, right? So you're certain to observe one of the eigenvalues of the operator. The question is which one? And so you're going to observe one of these with probability that's equal to the square of that coefficient. I think when I was talking about probability amplitudes earlier, I might have forgotten a square somewhere. But in general, like this Cn is like a probability amplitude, which is like a complex number, and we take its magnitude and square to get a real number that corresponds to a probability. Okay. And the last thing I'll say about this is for continuous spectra, reference Griffiths. Yeah, so you think back to the Stern-Gerlach experiment, it's like the two observables there are the spin aligned along the z-axis and the spin aligned along the x-axis. And the operators for each of those have different eigenbases, right? So going through one of the Stern-Gerlach apparati, is equivalent to projecting onto a basis vector in one eigenbasis. And then when you switch and measure along a different axis, you're switching the eigenbasis you're measuring across. And so you get a result that, now you're projecting onto a totally different basis that's orthogonal to your original set of basis vectors in this high dimensional space. And because they're orthogonal, you get this thing where okay, it's basically, after I measure in z, what I get when I measure along the x-axis is going to be random, right, like 50-50 in terms of which axis I get. Okay, any questions? Now we'll do some concrete stuff. So the last axiom of the theory is about the Schrodinger equation. So the Schrodinger equation is fundamentally an eigenvalue problem. For H, which we call the Hamiltonian, and the Hamiltonian represents the total energy of the system. So usually it's the kinetic energy plus the potential energy. And so the Schrodinger equation says basically just this. At a fixed moment in time. So you'll see this referred to as the time-independent version. Right. And so at any fixed moment in time, if we try to observe the system, we'll find an energy level that's one of the eigenvalues of the Hamiltonian with certain probabilities. And so commonly, this is going to look more like p squared over 2m. This term, so maybe I'll say this over here. So in classical physics, you have 1/2 mv squared. And let's say our potential energy is represented by some function that depends on position and time. Right? Then, just from the definition that p equals mv, we get that this is p squared over 2m plus v of xt. Right. And for a fixed moment in time, we're not going to consider v of xt, we'll consider v of x. And so this is how you might see the time-independent Schrodinger equation in context. Look at the problem we're going to solve today, whenever you don't have a time-varying potential. So here's the time-dependent version. So one axiom of the theory is that the Schrodinger equation describes the particle at all. Like we have this eigenvalue problem. And something that you really have to take as an axiom is the following, that I h bar del dt of psi of xt is going to be equal to the Hamiltonian acting on. Right. And so when we talk about stationary states in a couple seconds, you'll get a better sense for like what this really means. But this is an axiom that's like a priori, like left to its own devices. So like here's Hilbert space, or L2, and here's our state psi. And what this is saying is, if you're not measuring it, if you're not like prodding it and messing around with it, like the vector it's just gonna vibe, right? So there's some kind of like oscillatory motion here, like the I kind of indicates like a rotational kind of flavor here. And like left to its own devices, this vector, it's just gonna do its own thing. Its phase will probably change. And that'll really be it. Okay, so let me give you guys a better intuition for this. How am I doing on time? Okay. Probably gonna run out of time. So this is what I talked about just on the board I erased, where in this case where the potential is not dependent on time, we use the time-independent version of the Schrodinger equation, right? So if we have some big solution, capital psi, in this context, it turns out that we can solve the Schrodinger equation with a separation argument. So we can say little psi of x times some function f of t. Right. And so solving by separation. So I was going to do this for you, but I'm going to skip it for time's sake. So this tells us that f of t is just going to be e to the minus I e t over h bar. So this means that our solution to this equation, we're going to get solutions that look like this. Capital psi of xt equals little psi of x times this factor, e to the minus I e t over h bar. So when v of xt is just dependent on space, we have that the probability distribution. So maybe I should be more careful about what I say here. Right. We have solutions that only the complex phase will depend on time, right? And specifically, if I try and compute the probability amplitude, so this is going to look like this. This is the complex conjugate of this guy. And we're going to have e to the plus I e t over h bar minus I e t over h bar. And this is just going to be equal to the norm of psi of x squared. So the probability distribution, or the probability amplitudes, is constant in time. Hence, we call these stationary states. So this is probably the first takeaway for stationary states. And the second takeaway is that these states have a definite energy. And so I'll just jump to the conclusion here, which is that the standard deviation for the total energy, H for the Hamiltonian, is going to be 0. Like there's no variance at all in what you measure for the energy for a stationary state. Okay, is it okay if I go like 5 minutes over?
Sure.
Okay. So we're going to talk about the particle in a box. So this is more properly known as the infinite square well. So the fact that it's infinite means that your box has walls that are infinitely strong. So we have this potential. So it's 0 for x in a certain region, and it's going to be infinity otherwise. So this is going to look like this, where here's 0, here's A, and so our particle is allowed to live inside of here. Like here in this region, V equals 0, and outside of the well, we have V going up to infinity. Okay. And so here the potential doesn't depend on time. So everything that I said about stationary states applies here. So in particular, the Schrodinger equation says minus h bar squared over 2m. So here I'm plugging in the fact that the momentum operator is h bar over I times d over dx. So we have this is equal to d phi. In particular, this works out to just be this equation. If we define k carefully. So we let k just be this bundle of constants. And we recognize this guy. This is the same as the classical.
You want k squared there if you're taking the square root of everything?
Yeah, that's squared. Thank you. Yeah, this should be squared. And so we recognize this guy as the classical simple harmonic oscillator. And so we have a solution where these constants A and B are allowed to be complex. And so we have some requirements. So psi is continuous, CTS are continuous, and as for y, you can ask Griffiths. There's a proof of why we expect the wave function and its derivative to be continuous, but it's actually, I don't think it's straightforward. I think there's some argument there. And we also have, so this tells us that we have boundary conditions. So this is not a direct implication. Like there's some argumentation in Griffiths about why we should expect this to be true, and like why this implies these boundary conditions. But basically, because we have an infinitely strong wall, we expect that psi is going to be 0 out here, and we don't want a discontinuity at the endpoints. Like if it's 0 on the open interval all the way up to 0, then it better be 0 at 0, or else the function will be discontinuous. Right. So then we can use our boundary conditions. So psi of 0 equals b, and that tells us that b must be 0. Psi of a is A sine of Ka. And so this actually tells us that this number here, Ka, has to be an integer multiple of pi. And so we get solutions indexed by n. So these guys are indexed by z, and these ones are only indexed by n. And it's just because like sine of minus theta is equal to sine of theta. So we only get n index solutions here. And let me use what I know. So that tells us we have some quantized energy. So n is a quantum number. Right, so we found that only certain energies are allowed for the system, and they're indexed by this number n. And specifically, the last thing I'll say is that the normalization constraint, this tells us that the constant out front is going to be square root of 2 over a. Okay, so now let's think about these solutions. Right here in the middle of the board is good. This is x. So here's what side 1 looks like. Oh, so it's going to be 0 outside. So here's side 1, and this is the ground state. Here's side 2. So you'll notice that these are going to be alternatingly even and odd relative to the center point of the well. And here's side 3. So this one's even, this one's odd, this one's even with respect to the center point here. And the last thing I'll say is that these guys are called excited states. Right, so maybe I'll say that over here. Yeah, so side k, where k is greater than 1, not equal to, is an excited state. How am I doing on time? 3:51, okay. So these are excited states. I already mentioned that they're alternatingly even and odd. And the last thing I'll say is that the energy is proportional to the square of this quantum number. And this follows from the general observations we made about like the bases of like Hermitian operators like the Hamiltonian. But these eigenstates, these form a complete orthonormal basis for our Hilbert space, L2. And that's going to be true of the solutions to any problem like this. That's just a consequence of the formalism. And yeah, so now that we covered the particle in a box, in future weeks we can talk about like the quantum simple harmonic oscillator and then the finite square well. So in the future, so by the future I mean next week hopefully, instead of talking about like infinite potential barriers, we'll have something like this, where this is v of x, and it's finite. And so we'll have cases where we might have some wave function that's traveling towards the barrier. And so we'll also be talking about time-varying solutions as well. And we'll find that there's going to be a significantly large probability that this wave gets reflected, and there's going to be a tiny probability that it's going to come out on the other side of the barrier, and that's the whole quantum tunneling story. So, yeah, that's it.